Welcome to the Fairbanks Museum's virtual classroom. Our upcoming class is Forces in Motion. It'll be taught by STEM Lab Director Leila Nordmann and Science Educator Hannah Buckner. You can, if you're joining us live on Zoom, if you want to ask questions, you can do that in the chat function, and we'll be monitoring that and sending those questions to Leila and Hannah. You can also watch this live stream to YouTube, and if you do have questions there, you can email me. My email is akane, K-A-N-E, @fairbanksmuseum.org, and we'll try and get those questions answered for you. So we're going to give just another minute or two for last folks to join, and then we're going to start our class right away. Okay, let's go ahead and get started.
Great.
Great. So this class is Forces in Motion with Leila Nordmann and Hannah Buckner. So if you're watching this on Zoom, you can ask questions in the chat function, or on YouTube Live, you can email me questions. My name is Adam Kane. My email is akane, K-A-N-E, @fairbanksmuseum.org. And if you're watching this on Kingdom Access TV or another community access affiliate, welcome to the class. Please keep in mind that this class is recorded, so anything that is broadcast here is subject to rebroadcast. And thanks so much for joining us today, and I'm going to turn it over to Leila Nordmann.
Great, thank you so much, Adam. So today our class is going to be looking specifically at Isaac Newton and his 3 laws of motion. I'm going to go through those 3 laws with some demonstrations, and then I'm going to turn it over to Hannah towards the end, because I would love her to talk about how his laws apply not only to us, but to our solar system and the universe. So to start with, I'm going to go ahead and share my screen. And so here we've got Isaac Newton. This is before he became Sir Isaac Newton. This is during actually his college days when he went to Trinity College in Cambridge, and this is over in the UK. And interestingly enough, something happened to him that we are currently going through, but instead of a virus where he was, where he needed to sort of shelter in place, it was actually the bacteria that caused the plague, so the bubonic plague. It was one of the last major outbreaks in 400 years of that plague. So what he did in order to shelter in place is actually his college, like many of our schools, closed. And since it was near London, which was a major city center with lots of people, and he moved out to a place called Woolsthorpe, which is this building right here, out in the countryside, about 60 miles away, in order to socially distance himself from other people. And interestingly enough, in that time, so it was sort of a year and a half that he was there. This is during 1665 to 1667. So just realizing this is, over 400 years ago. He spent time there, and he actually considered it his years of wonder, or sorry, his year of wonder. So he actually wrote a paper called the Annus Mirabilis, which is, again, in Latin, the year of wonder. And in that time, he actually wrote papers on what would become early calculus. He practiced with prisms and optics, so using those windows and natural sunlight coming through those windows in his house to play with optics and prisms. And then he started thinking about gravity. And so one of the stories is this the place where the apple fell on his head? And here, thus he's discovered gravity. The real story is that he may have actually just seen an apple fall outside of his window, or when he was outside taking in the fresh air. And that led him to think, or start to question, how does the universe work? And really started thinking about the forces of gravity. And so to realize he also studied those who came before him, like Galileo and Descartes. So he's basically, as he's coming up with his theories and spending this year really thinking things through, he is also saying that he stood on the shoulders of giants. So he took everything that people had sort of compiled, observed about the world before, and he continued to work on them. And with this knowledge, he eventually, about 20 years later, wrote this book called The Philosophia of, or Naturalis Principia Mathematica, which also included classical mechanics. And this is the thing that we're sort of primarily going to be looking at. But classical mechanics is the science concerned with the motion of bodies being acted on by forces. So any body, from, you know, the earth as a body, from your body, from a tennis ball, from a tree, all of these various things, and what forces can act on them. So with that, I am going to stop sharing my screen and hopefully give you a view of my table here. And the idea is, my first question is, I have this ball here, and we kind of have to go back because we're going to look at his laws, but we sort of first have to look at, you learn various motions or forces through push and pull. So if I ask, like, how would you move this ball? You might say, well, I could push it away from me. I could pull it towards me. And those are forces that you can enact on this ball or various other things. You may, you've learned push and pull from a very young age. You learn pushes like to throw or toss or kick a ball, and learn pulls maybe to bring a soccer ball back towards you to go around a defender, or when you're playing basketball to bring the ball back towards you. So in every day in your house, you may be pushing and pulling. You may be opening windows, closing doors. And then even air pressure can be a push and a pull. I think of a vacuum as a pull, but then if I wanted to move this ball using air as sort of the mass and the force, all right, hold on. I'm going to use a lighter ball. With that idea that I can move it. So the mass of this, I needed a lot more force, which I did not have to enact on that ball. So from this, we began to understand that Newton's first law, so I'm just going to throw it up there really quickly, and then we'll should be able to move forward here. So Newton's first law. So this is exactly how he wrote it, but then we'll sort of talk through it. Every object persists in a state of rest or uniform motion in a straight line unless it is compelled to change that state by forces impressed on it. So that seems like a lot of wordage for something that we hopefully can show a little more simply here. So again, that idea that force is acting on it. We have that push and that pull, but then we notice that it wants to just sit here and stay. So what are some of the other forces that might be acting on this ball right now that are basically showing, you know, its object speed is not changing unless something acts on it and makes it change. So if it's going to stand still, it's going to stay still until something acts on it, like myself. So I don't know if anyone has any answers for me what else is acting on this ball, but one of them is gravity. And then the other one, is friction. And friction is something that you could do right now at home. You could rub your hands together really fast, and that kinetic energy is going to transform into heat, and you're going to be able to feel that. And the longer you rub your hands, the more you're going to rub the dead skin off. And eventually, if you rub for too long, A, they're going to get very, very warm, but B, you're probably going to get some blisters, which isn't going to be so awesome. But you can also feel that there is friction not only with your hands rubbing together, and you have to force because otherwise that friction wants to slow them down. But if you do this, you can actually feel the friction of the air. So you could do this for a lot longer. You might get very tired, but you can feel that air force around you, or the friction of the air. So these are other forces, not just the push and pull, but the gravity's force and the force of friction acting on this ball. So thinking about some forces you might have to use, I would think about like at home, if you had a wheelbarrow, pushing that wheelbarrow and seeing how much force it needed, and then filling it with a ton of rocks, like as many rocks as you could find, and then going and pushing it again, realizing you're going to need more force to push that. But also, if you come to a hill and it's full of those rocks, you may need that pull sort of back, because it's going to continue moving in that line. So you want to, there's forces acting on it to either have it slow down or speed up. And those are the forces you can use. And same as if you go to the grocery store, you're pushing a cart. When you first go into the grocery store, that cart is empty. You might be able to push it just with one hand. But at the end, once you filled that cart, you realize you need two hands, and you need to either really push with a force or really pull so that you don't run over the person in front of you with that heavy cart. But one other thing that I want to show you guys, and this again is something that you can do at home, and I'll put into the sort of resource notes that we put together, is this is a nice way of showing that, you know, this object speed will not change unless something else acts upon it. I have a raw egg with the letter R on it and a boiled egg. And so I want us to look, let me see if, realizing you guys, okay, seeing this motion. So our boiled egg, which essentially is solid, when I spin it, it spins very easily. And if I put my finger on it, it stops. It's got a little bit of motion, but it stops. So I'll try doing that one more time. So, whoop. And so we can get that to stop. Now we take the raw egg, which again, just like this egg, solid outside, but liquid inside. Let's see what happens. First of all, I tried to spin it, it spinned a lot more slowly. And then when I try to stop it, it actually continues spinning. So getting it going, same force with that egg, but much slower. And then when I stop it, it still continues. That yolk hasn't stopped moving, even though the outside has, and it continues to spin. So I think of it as if you were in a car and you didn't have your seatbelt on and some motion came to stop you, it would be like the egg, the raw egg. You would stop it, but the inside, the people would continue to move if they weren't wearing that seatbelt. Whereas if you're wearing that seatbelt, this solid car going quick, it stops. Oops, it wants to roll, but hold on, let me see if I can do. It sort of stops in place. So this idea that you're not, the liquid is no longer moving. So everything inside is no longer sort of loose, it's solid. And so this is something that you can do at home, seeing how that inertia, something that's in motion wants to stay in motion. And so that egg will continue to spin versus this one, which is more solid, and I can actually stop. So that is one way that you can test out sort of that first law at your house. But another thing that I wanted to show you is Galileo. Again, remember Newton was getting his ideas from people who had done this before. Galileo studied numerous bronze balls. So he took of various different mass and size and everything. And what he realized is if he watched for 1 second intervals, he could see that they both roll at the same speed every time. Didn't matter size or weight. They would basically, the rate of descent remain constant every time. So he figured that free falling objects would experience uniform acceleration regardless of mass. So this is again something you can try with, various different sized balls at home or different weights. And you could actually, with a slow motion camera, which is the next video we're going to look at, you could actually see and slow down that motion and see what Galileo was actually talking about and what Newton was building on. So let me bring this forward, and what we'll do is we'll go back. Oops, need to share the screen. There we go. All right, so our second law is, this is how he wrote it up. Force is equal to the change in momentum per change in time. For constant mass, force equals mass times acceleration, which is right here, this equation. And sorry, I just want to get, so force being the push or pull exerted on an object, mass being a measurement of how much matter is in that object, acceleration, how an object's velocity changes over time, and velocity, similar to speed, the distance which an object travels in a certain amount of time, and then momentum being a characteristic of moving bodies determined by the product of the body's mass and velocity, which is something that we'll look at in a few minutes with this last law. But here, this idea that a net force acts on an object and the object accelerates in the direction of that net force. So what we're going to look at is a video slowed down where Bobby is dropping two weights. So the force is going to be gravity pulling it down to the ground, but the mass is going to be different. One of the weights is 50 pounds and the other weight is going to be 1 pound. So the mass is 50 times greater than the other one. And what I want you to notice is, do they fall at the same rate? Because we just learned that they should accelerate at the same speed and fall at the same rate. But let's look at the force that the 50-pound one hits with versus the 1 pound. So, and I'll play this twice, but here's our video. So here he is, he's lifting. You can see the 50-pound weight easily. And then the 1 pound weight is in his other hand. 4, 3, 2, 1. So in slow-mo, you should see they're dropping at the same time, at the same rate, but now look at the force. And I'll play it one more time and I won't talk because you can actually sort of hear it at the end hitting. So let me.
This is tougher than the middle for sure. 5, 4, 3, 2, 1.
So you can hear the larger one with that more force. It actually made a huge dent in the ground when we went over there to look, but it hit a rock and you can hear that when it hits, you can hear that force or that mass hitting. All right, so any questions? Do we, at this point? If not, that's okay. We'll go on to the next one and we'll go on to the third law here, which is
we're gonna have questions at the end. We're gonna have a question period.
Okay, perfect. All right, so I'll go through the third law and then let Hannah speak a little bit, and then we'll do the questions. Perfect. So this one might be the one. So that equation is very famous in physics, the second law that we just looked at, but the third law, for every action, there's an equal and opposite reaction. I feel like a lot of people have heard that before. And so this is where you're basically looking at, for every action, there's a reaction, a force exerted by one object on another object, involves actually the interaction of those two objects. So the first object is going to exert force on the second object, but the second object will also exert that force on the first one. So one way you could think about it is, think about a baseball bat hitting a baseball. So that baseball bat has a lot of force. It has a person behind it, and it's hitting that ball. And as it hits that ball, you can hear it. You can also feel it in your body as you're swinging that bat and making contact with that ball. And of course, that ball's reaction is now being pushed away. But we do realize even that small mass of that ball at times has a lot of force because it can break that bat. So it's just thinking about also even just some basic forces. So let me stop sharing the screen for a second and just looking again to this idea of sort of the Earth's gravity or the force of gravity on this ball. It's not moving right now. And the tennis ball's weight is actually a measurement of Earth's gravitational attraction. So the force is straight down towards the center of the planet. But despite this force, the ball remains motionless. And why? This is because the table is another force pushing upward equal to the weight of the ball. Now, if the ball weighed more than the table, it would crush the table and it would go down to the floor. The floor would be the next force pushing up against the force of gravity. So this is, equal and opposite forces reacting on this ball. But the last thing I want to show you actually is something called a Newton's cradle. So we're going to look at the motion of that and the three main physics principles: conservation of energy, conservation of momentum, and friction that is happening to the objects or the spheres, these metal spheres in that. And right before I do that, I did want to share out one thing I thought was really neat is the force of our own bodies, vehicles, excavating, mining, fracking, various different things that we do on the Earth's surface. Because we've stopped doing all of that stuff for right now during this time of this virus, the seismic activity and readings have actually gone way down. So we're actually starting to read what the Earth's normal forces are without our forces acting on it and disrupting that read. And I just thought that was a really neat thing that's happening during this time when we're all sequestered and we have to, not move around as much. It's actually, we're seeing the force of humanity on the Earth lessened in some way, and being able to read more of the Earth's own internal forces. So I just thought that was a really neat thing that I had just read. All right, so let me go ahead. I'm just going to share my screen one more time for those last videos. All right. So the Newton's cradle is just something that someone developed in the 1960s. And it's basically, again, to show these three physics principles. But what we're going to go show first is just how it works. So you pull back the ball. And then I want you to notice how the energy is being, it's not created or destroyed, but it's actually moving through. When this ball hits, it's transferring through and then pushing out that final ball. So let's go ahead and look at it from a top view, just to give you a different view here. So again, pulling it out. And if the balls were completely uniform in size and there wasn't friction or vibrations, this actually would never slow down. They'd have to be the same weight, exactly uniform and perfect spheres. But this idea is this could go on forever, except that one force slowing it down, just kind of like we talked about earlier, is friction. But the friction is actually the molecules vibrating inside each one of these spheres and turns kinetic energy into heat. So that energy isn't lost, it's just been transformed. So let's look at a slow motion here of what happens, just to be able to see the energy traveling through. So we've got our potential energy using gravity, he's gonna let go, and then it's turned into kinetic, which is transferred through each one of those balls, or spheres, metal spheres, but each one of those metal spheres is also vibrating now on the inside. And so the impact of one sphere will move the other of the same mass, the same distance at the same speed. So it could go on forever, except for that friction.
So Leila, we have a question. What would happen if you moved multiple balls to start?
That's a great question. So if some of them go up to 7, or it's best if they're odd numbers. You'll notice this is 5, but you could take 2 of those balls, swing them out. They will hit the middle ball. And just like when a pool ball hits another ball really hard, the ball stays in place, the other ball moves, it's a transfer of energy. So those other 2 balls beyond the one in the middle will get kicked out the same distance, same speed, because it's the same mass. So you can do it with, you could keep building out your cradle, and have 11 balls. So you could do 5 moving in one direction and you'll see the same thing. It's going to kick out those 5 on the other end.
Is there a limit to how big those objects could be before the physics stop working?
That's an awesome question. I honestly, I don't know. I was thinking of trying to build this for myself. Oh, Hannah has an answer.
So essentially any size would keep working as long as you just have the right like pendulum thing to hold it, because there is no limit to when physics stops working. It's always working. There's no change in whether or not a size of a ball would stop working as a pendulum.
Awesome. Well, thank you. And maybe this can lead right into sort of how these three laws that we've tried to look at in different ways work within our solar system and our universe. If you want to go ahead and take that away for a few minutes.
Sure. So yeah, oh, Leila, if you don't mind unsharing the video.
Oh yeah, sorry, my bad.
No problem. So yeah, these three laws are quite literally the building blocks and the foundation of how the universe works. And so I thought it'd be a really good idea to kind of show what it looks like to have our solar system moving, but I just have to, give me 1 second. Later. Okay, so let me go to Zoom. Okay, I'm going to share my screen. And I want to just show you this solar system simulator real quick. If I can move it. Ah, where'd it go? Sorry, guys. There it is. Okay, so this is really cool because it actually shows what our solar system looks like in like really good detail. So you're seeing all of these planets that are, you know, moving around in the solar system. We're seeing it slightly sped up, and as we move forward in time, we're seeing that they keep moving and they are orbiting our sun, and you see that the asteroid belt is moving and all the other planets are moving, but some of them are moving slower than others. And actually, if you might be able to see it, may not be, but the sun actually has its own orbit. So all of our solar system doesn't necessarily move just around our sun, but the sun is moving around this fixed point called its center of mass. And so it's not in the sun, it's slightly distant from the sun. And this is because all of the different masses of the planets, the comets, the asteroids, all of them have a mass that puts a force on the sun. So just like how if you push a stationary ball, it's going to move, or when you're in a car and the car is going around a bend and you're feeling yourself being pushed, it's just the same way with the sun. And so because you have all of these masses and they're pulling and they're spinning around with the sun has a motion. So that is equal and opposite reaction. They're all exerting a force on each other. Also, we're seeing that these planets are moving in a fixed orbit, their own little orbits, whether that's in a flat line or you have an orbit like Makemake or Pluto. They have angles, but they're going to stay that way unless an asteroid hits them, or maybe something happens and something intercepts them and changes their orbit. That's why we have the International Space Station staying in a specific height above our atmosphere, because they're in a fixed motion. If they change the way that they are fueling their energy, or if they change the angle, it could change how fast they're going or the direction that they're going. And so this is how the entire universe actually works. There are interactions that we see, and it impacts how everything forms. And so, yeah, that's essentially how the universe is working in
Awesome.
general.
So we're seeing kind of that first law that the object's speed will not change unless something else acts upon it. So everything is moving, and gravity's force is acting on it out there in the solar system. But as long as it maintains a certain speed, it will stay in orbit, or as long as something else doesn't hit it.
See that these forces are greater, or the amount of gravity that we're feeling with certain different bodies are due because of their mass. So we know that gravity is a force, and so therefore a force in terms of gravity, it's not just acceleration, it's a force downward. And so you have that. So when you have a thing like the sun, there's going to be more gravity or more force because it's so massive compared to Earth.
Great. Awesome. Well, does anyone have any questions at this time? I want to keep it within the half hour that we promised, but we just want to find out if there's anything right now that you would like to ask or are curious about while you have us on. Otherwise, we will have a resource page. I'm going to put a couple of videos. Hannah sent me some information, so that'll all be on that page, but also, the boiled egg versus the raw egg, and how to do your own experiment, sort of dropping something from a height. I'm not going to recommend a 50-pound weight, but maybe something smaller like a tennis ball and a crumpled piece of paper, and make sure your pets are out of the way. But yes, there's things that you guys can do at home to test out all of these principles, but also, or theories and laws, but also to realize that they're acting on us in the universe as well. So we just wanted to share all of that out. But I don't see any additional new questions. So if everyone's good with that, we've had a great class.
We just had a question come in, Leila. How long have we known about gravity?
Oh, Hannah, do you I mean, well, certainly since the 1600s, because Galileo was testing it.
We've always known that we are on the Earth, but it wasn't really until Newton that we thought about gravity, because there was this idea, and actually many people still have this idea, and it's kind of interesting that people still think this, but when the world thought the Earth was flat and that everything moved around the Earth, everyone just thought that because we weren't spinning, that if we were spinning, we should be flying off into the atmosphere. So that had to be why we were on the ground, not that because we had gravity. So that really, the general accepted thought of gravity hasn't been around for that long. It's only been around for about 300, 400 years. But there have been individuals who have thought about gravity and having this radical idea, having a scientific revolution, like Copernicus or Newton.
Well, and this idea that you could stop believing in gravity, but it's still going to act on you no matter what. All right. Anyone else with any questions? That was a great one. Thank you. All right. Oh, maybe there's one popping up.
Nope. I think that's it. Oh, here we go. No, we did just get one.
Okay.
What is under the Earth that causes gravity? So what causes gravity?
That is a good question. So it's not anything specifically under the Earth that causes gravity. It is just the fact that the Earth is so massive that we have gravity. I mean, actually, you and I have gravity. If we were in space and we were floating around like this and we were near each other, eventually it'd be very small, but we'd actually float towards each other because we have attraction. Gravity is a force of attraction. And so any kind of body can have it. It's just that, smaller bodies, it's not necessarily detectable because gravity is actually such a small force. But it just has to do with the fact that the more massive a body or object is, the greater the gravity. That was a really good question. Thank you for
And I see
asking.
someone said, how long has Newton's laws been around? He wrote that principle of Mathematica, which had those laws in it in 1687, so over 400 years ago. But thinking again that we all sort of know certain forces are acting on us, it was just the fact that he could encompass them in these laws that then also made sense, because as you went from Earth to the solar system to the universe, they all still worked on each other all the way through. So
I think it's important to note that these laws that we have, or understandings in science, they're not things that we have said this is a thing and then created it. They've always been around. It's just people have discovered a way to recognize them, measure them and say, this is something that keeps happening. And so we're going to say that this is something that we need to study. So the laws that Newton had came up with, they've been edited and adjusted for different things in more advanced physics or astronomy, but they've been around since the Big Bang. And before that, we don't know what was around. So they've been around for your entire life and the entirety of the universe.
Awesome. Well, thank you guys so much. It looks like someone said, nope, no more questions. So maybe they're calling it a day. But again, if you guys want to email us, or we'll certainly have the resource page up on our website. And we would love to follow up on any questions that you may have. But again, hopefully these are things that you can try at home, just to try out those laws and theories. And we really appreciate you joining us today. So thanks so much.
Great, thank you. STEM Lab Director Leila Nordmann, Science Educator Hannah Buckner. Thank you guys so much. And for everybody watching this, stay safe out there. And we look forward to seeing you at the Fairbanks Museum soon. Thank you.